Right, we're now going to look at some more examples in relation to Le Chatelier's principle. We're looking at decreasing pressure or increasing pressure, or decreasing volume or increasing volume. We'll also look at the effect of heating and cooling on the reaction mixture. So let's look at an example of that. We've got an equilibrium situation. This is something that I've made up. We've got 4 SO2s, 4 O2s, and 6 SO3s, so I'm just saying that that's what the equilibrium is. If we add up all the numbers, if we add up all those molecules, we'll come out to 14. So that's 4 plus 4 plus 6 is 14. We've got the reaction in a piston. That means that we can increase the volume by lifting it up or decrease the volume by pushing it down. There's an inverse relationship between volume and pressure. What we can say is that by increasing the volume, we're going to decrease the pressure, and by decreasing the volume, we're going to increase the pressure. Now, if we lift up the piston, we're going to increase the volume, which has the effect of decreasing the pressure. Now, what's going to happen is the reaction will respond by trying to fill the extra space with some more molecules. So what's going to happen is that the reaction will move to the reactant side, that is the side that has more gas molecules. So here we've got 2 gas molecules on the product side and 3 on the reactant side. So what I can do is I can actually take 2 SO3 molecules and convert them into 2 SO2s and an O2. That's what the reaction says. I've got 2 SO3s, they can be converted into 2 SO2s and an O2, and that's what I've done here. I've taken these 2 SO3s and converted them into 2 SO2s and an O2. Now the effect of that is I've now increased the number of molecules in the reaction to 16. So you just add all those up, you're going to come out to 16. So that's what's going to happen whenever we increase volume or decrease pressure. The reaction is going to respond by going to the side that has more gas molecules, and the way you can look at that is to fill up the extra space that we've added by increasing the volume of the reaction vessel. The other thing that we can do is we can decrease the volume or increase the pressure by lowering the piston. Now, in so doing, what's going to happen is that the reaction will shift to the side with fewer gas molecules. And what I've done here is I've taken 2 SO2s and I've converted them into two SO2s and an O2 and converted them into 2 SO3s. And that's what we've said the reaction can do. 2 SO2s plus an O2 gives 2 SO3s. And that's what I've done. I've taken the 2 SO2s from here and an O2, converted them into 2 SO3s. Now when I did that, what happened is now the number of molecules in here is going to be 13. And that means that we've decreased in total the number of molecules in the reaction vessel. Now the reason we've done this is because now we have less space, so the reaction is responding by trying to form fewer gas molecules to account for the less space that we have now that we've lowered the piston. So that's the way you can look at it. The other way you can look at it is you say you're kind of squashing the molecules together and forcing them to take up less space, and therefore the reaction will shift to the side that has the fewer gas molecules in that situation. If it turned out that the number of gas molecules wasn't changing, going from the reactants to the products or products to the reactants, then increasing the volume or decreasing the volume would have absolutely no effect on the equilibrium. So now let's look at the effect of adding or taking away heat from a reaction in relation to Le Chatelier's principle. So let's say this is our reaction. We've got heat on the product side. That makes it an exothermic process because heat is being released as products are produced. Let's take a look at an example of this. So let's say we added heat to this process. Adding heat would mean that we were adding a product, and adding a product would move the reaction towards the reactant side. The way you can look at this is that the reaction will move towards the reactant side to use up the extra heat that we're adding by forming more reactants. Cooling the reaction means we're removing heat, and removing heat would mean we were removing a product, and that would mean the reaction would move towards the product side. And the way you can look at this is that the reaction will will create more heat to counter the heat that we removed by cooling the reaction. So cooling would remove the heat, removing the products, pushing the reaction towards the product side. Now if we change the problem by putting heat on the reactant side, we make the reaction endothermic. And by making the reaction endothermic, Adding the heat is like adding the reactant, which would move the reaction towards the product side. And the way you can look at that is that the reaction will use up the heat, extra heat we're adding by forming more products. Cooling is going to be removing heat, which is like removing a reactant, so the reaction will move back towards the reactant side, again to replace the heat that we've lost by cooling the reaction. And all of these wordings here would be the appropriate wordings to use when given any of these instances in the exothermic or the endothermic cases.